Hello, everyone. Today we have Vitaly Feldman. He's a research scientist at Apple, and his research field is the foundation of machine learning and privacy preserving data analysis. He received his Ph.D. from Harvard, and he was previously a research scientist at Google Brain and also IBM Research. Today, he will talk about low communication algorithms for private federated data analysis with optimal accuracy guarantees. So without further ado, I invite Vitaly to start his talk. Thank you.
Thank you, Mariam, and hi, everyone. It's a pleasure and honor to give a talk at your seminar. As Mariam mentioned, I'm going to talk about understanding of this trade-off between achieving low communication, and while also achieving optimal trade-off between privacy and accuracy guarantees. Let me start sharing my screen. Share. Okay. Everyone should see it fine. No? Okay. So please feel free to interrupt me with any questions you have during the talk. I probably won't see you. At least I don't see most of you. So yeah, just please interrupt even while I speak. No worries about this. So let me start with describing the basic setup that we'll be looking into. And that is so-called federated data analysis, or we'll be specifically looking at the private version of it. And in this setting, we have a bunch of clients. Think of your phones, each holding a data point, and we'll denote those data points by x1 through xn, where n is the number of client devices. And we have a server that wishes to perform some kind of data analysis on the data held by the users. For example, build a histogram, train machine learning, and so on and so forth. There are many important tasks which a server may want to solve so as to improve services such as smart assistant, predictive keyboard, recommendations, and so on and so forth. There are many tasks or data analysis tasks that one typically wants to solve, but most of those boil down to solving two basic primitive tasks. The first one is frequency estimation of building a histogram. It's again, a standard task in which we think of each user as holding a number between 1 and k. So the domain is of size k. And the goal is to estimate the frequency, just in like the empirical frequency of each of those k elements in the data sets, which is just this expression. And the notion of which means that we want to produce some kind of estimate. Let's think of those estimates as f tildes, f from 1 through fk. And we'll be thinking of, for simplicity, just minimizing the expected squared error of the estimates that we produce. Again, one can think of infinity error and other notions. This will not be actually not particularly significant for almost anything we will be saying in this talk. The second basic task that one needs to solve in federated learning is typically referred to as L2, high dimensional mean estimation. And in this task, we think of each data point held by each of the users as a vector in a d-dimensional space. And we'll typically, and for simplicity, assume that the norm of that vector is upper bounded by, say, 1. And the goal is to just estimate the mean of all those vectors held by the users. And again, we will want to, estimating here, we'll think of in terms of expected squared error. And this is the task which is sort of central to solving, to training machine learning models, because as you all know, we train machine learning models by doing some type of gradient descent, and that requires estimating gradients, and gradients are just high-dimensional vectors. So pretty much training machine learning pretty much reduces to this solving this task iteratively. So I mean, these are super simple tasks by themselves, but what makes them harder is that the data held by users is often sensitive. Well, I mean, again, I don't need to convince in this seminar that that the data held on phone devices can be sensitive, and the users may not be willing to send it sort of directly, allow the server to have this data and store it. So we'll be interested in solving these problems while preserving some notion of privacy, and specifically the notion of privacy we'll be looking at is the local differential privacy, which again, as probably most of you know, has originated in social science. This has been used in some form by Warner. Has been proposed as one of the privacy mechanism by Efimevsky and others in 2003, and then translated to the language of differential privacy by Viswanathan and others in 2008. And this notion has since been adopted both in theory and in industry. And basically it requires that each client runs an epsilon differentially private algorithm on its data and then sends the report to the server. And what does it mean in this context to run an epsilon differentially private algorithm is basically a randomizer, which takes the input and has whatever the data point, and has the following property that for any two different possible input points, and for every point in the output domain of the algorithm, the probabilities that that output element is output under the two different elements are the ratio of these probabilities is at most e to the epsilon. And you just think of it as, again, the ratio of these output densities or probability mass functions is with an e to the epsilon. Another way to think of it is sort of how much you update your prior based on observing any output. Your prior will not change by this, at most, this factor e to the epsilon. So, of course, we will measure this epsilon is the privacy parameter. And I think I should mention that we'll be focusing on the value of epsilon, which is a small constant, which is larger than 1, such as, for example, 5 or 8. And maybe this is relatively large by the standards of the centralized differential privacy. But in the context of federated learning, such epsilon can be justified simply by adding, by ensuring that in addition, sort of these reports are shuffled and anonymized before being delivered to the server, or certainly before being stored. And we now know that such shuffling has an amplifying effect, and basically with sort of a sufficiently large number of users, one can amplify from these small constant epsilon to basically very small epsilons below 1. So as mentioned, we want to be able to solve these mean estimation and frequency estimation tasks while satisfying this notion of differential privacy. And these are not new problems. Said these are indeed basic questions, and the model itself has been studied for over a decade. And there has been quite a bit of work, but perhaps it can be summarized briefly that existing approaches have one of the properties. Either they achieve this optimal trade-off between privacy and accuracy. Accuracy here, that is in terms of the notion of error I have mentioned, or methods, they either achieve this or have low communication. Sort of the methods all methods that achieve the optimal privacy and accuracy trade-off have communication cost that scales linearly with the dimension in the case of the mean estimation and the domain size in the case of frequency estimation. Both of these can be very large. Naturally, domain sizes can be huge, and even dimensions are typically very large when one trains machine learning models. So this communication cost is actually prohibitive in practice. So basically what one ends up doing is having to sacrifice the, somebody is drawing something. I'm not so sure how is that, but whatever. Happening. But basically, one has to sacrifice the trade-off between privacy and accuracy. And to be clear, optimal here, I mean optimal to the constant, not just asymptotically optimal. And this notion of optimality up to the constant is actually crucial, again, in practice, because it translates into meaningful improvements in accuracy of downstream tasks. So now let me go into a little bit of detail about known approaches for at least some of the known algorithms for both of these tasks. So let's start. Okay. Let's start with frequency estimation. There, maybe there is one of the standards and simplest algorithm was first introduced in the work referred to as Rapport by Erlingsson et al. It's a very simple algorithm, and I'll describe it actually later in my talk, which achieves optimal trade-off between error and privacy parameter, but it has communication costs, which is K being, again, the domain size. In addition, has poor server runtime, but communication is the main concern for us. There is also a somewhat better algorithm, which is referred to as subset selection, a very similar algorithm, which also achieves optimal trade-off. That one is optimal even up to the second order terms. And here, maybe I should mention that optimal, we even know the rate of the sort of the error of the optimal algorithm, and it looks as follows. It's not so important for this talk what exactly this expression is, but that's we happen to know the expression for optimal error. So this algorithm has somewhat better communication of K over e to the epsilon, but still scales linearly with domain size and typically is very large in practice. There is several algorithms that for this task have been developed in the context of heavy hitters, where one basically only wants to discover the elements that have sufficiently high frequency, and sufficiently high sometimes is defined in various ways. These algorithms are known to achieve order optimal trade-off between accuracy and privacy. And again, the ones which were introduced initially only did it for epsilon, which is smaller than 1. There is some kind of phase transition in this dependence on epsilon at epsilon being equal to 1. These algorithms do have optimal communication, like very low communication, just logarithmic in K, and also low server time. But again, these are initially were only known for epsilon smaller than 1. 2 algorithms based on Hadamard response have been proposed, which in around year 19 and 20, which achieve again order optimal error now for all epsilon, and they have both low communication and low server compute. And maybe the only algorithm which sort of was known that sort of reconciles these low error with low communication is so-called local hashing by Wong and others. It achieves optimal error, although only for some fixed sending of parameters, and achieves low communication if one allows a lot of public randomness, which is, again, if you want, in some settings might be fine, but in the setting where you also want to anonymize the reports doesn't really work. Again, there are some fixes that they introduce some other issues. So it's also is not maybe ideal for practical purposes. So let me now describe the state of the art for mean estimation. There, maybe the most basic and well-known algorithm for doing local randomization of d-dimensional vectors to add Laplace or Gaussian noise. It is actually known that this would achieve order optimal error, although in this case, it's these algorithms don't achieve pure epsilon privacy. Order optimal error, which is, by the way, the expression is here, is only achieved if one basically with epsilon with approximate version of differential privacy, which makes things slightly worse. Introduce some log factors, and they also have high communication. The communication scales with the dimension. Of course, you output the entire vector. It's order. It's basically d integers. The first algorithm which achieves this kind of, which is order optimal for pure epsilon, was introduced by Ducci and others, and maybe it's informally referred as private half space. It's not so important, but it's a slightly different way to randomize. It's order optimal also only for epsilon less than 1, and still has very high communication cost. Although that one, there is a version of this algorithm that has lower communication. Finally, the first algorithm which achieved the order optimal error for all epsilon is the algorithm PrivUnit. I'll describe that one in more detail later, by Bolmick and others. Still has high communication of order D. Finally, there have been the only algorithm which have low communication, and in this case, low being again exponentially smaller, it's order epsilon times log 2D, have been based on so-called Gaussian representation of vectors. First in my work with Guzman and Vimpala, and then more recently for all range of epsilon by Chen and others. And these again achieve order optimal error, and these algorithms are the first ones which achieve low communication, but can also have low server compute. So that's the state of the art. It was not known whether any of these algorithms is actually achieves optimal trade-off between privacy and accuracy, truly optimal up to a constant. Although, as I'll describe, we now know which one does. But empirically, the best constant was achieved by this PrivUnit algorithm of Bolmick et al., which does have worse communication, has poor communication complexity. So that's the state of the art. Now I can finally ready to describe the results that I would like to mention in this talk, and those are written several works on this topic. So the first one, and which I'll probably spend the most time on, is a general lossless, we call it compression of efficient local differential private randomizers. Basically, this is a result which says that if you have a local differential private randomizer which is efficient in some sense, basically computationally efficient, then we can replace it with different randomizers without any losses in privacy or utility, which at the same time has low communication. So no matter how large the communication was initially, we'll get low communication protocol. So for any local differential privacy protocol, there is a way to reduce its communication. It's not compression in the regular sense of the word, and that's why it's in quotation, because we are not compressing the original the original message. We are replacing it by a different message, which is indistinguishable from the original one after certain decoding. So based on this general technique, we have two applications. The first one is algorithm which we refer to as Rapport, which is a simple and optimal randomizer for frequency estimation with low communication. And also we have application to this mean estimation problem, where we show that one can first of all get a compression using the general technique, plus one can have achieve certain trade-off between the achievable error and the running time using repetition. I'll describe the algorithm later. So this Rapport algorithm is for frequency estimation is sort of improves communication, but it's the server runtime is still kind of becomes sort of a bottleneck at that point. And I'll briefly describe an algorithm from a joint work with Jelani Nelson, Huyen Nguyen, and Kunal Talvar, which is referred to as projective geometry response, which in addition improves the server running time. It uses a different randomizer that achieves much better running time than Rapport. Finally, I'll describe the work with Hilal Assi and Kunal Talvar, in which we prove that this algorithm priv unit actually is, for appropriate choice of parameters, is optimal randomizer, and basically because we know that it's optimal and we can compress it, we'll be able to get an optimal algorithm with low communication. We also show that there is a variation of that algorithm, which is called Gaussian version of the priv unit, which is somewhat easier to work with and still achieves optimality, although I won't have time to say much about this algorithm. So that's the overview. Let me know if you have any questions so far. If not, I'll just go ahead and start. I'll spend most of my time describing this general lossless compression scheme. All right, if there are no questions so far, let me describe the sort of, first of all, this main result. Basically, we start, we basically show that for every epsilon differentially private, computationally efficient local randomizer R, which maps from, think of from X to some output Y, there is an efficient epsilon differentially local randomizer R prime, which now maps from the same input space X, but to domain Z. And we should think of Z as seeds to some pseudo-random number generator, PRG. And together, we also have some kind of decoding procedure, which decodes from these seeds, replaces maps each seed to an element in the output domain with the following property. Once you apply the decoding procedure to the output of this randomizer, the resulting output is computationally indistinguishable from the original randomizer. So basically what we get here is that we replace the original randomizer with a randomizer which has a smaller space Z, just it sends some kind of seeds to a PRG. It has still the same privacy guarantees. We started with an epsilon differentially private randomizer, and we ended up with an epsilon differentially private randomizer. And in addition, their outputs are computationally indistinguishable. So what we have gained is that we are now sending only this seed in the space of Z. So the question, of course, is what can we say about it? So theoretically, sort of under sufficiently strong cryptographic assumptions, we basically get that the seed that needs to be basically logarithmic or polylogarithmic in the problem size that we're considering. So it will always be small theoretically. Typically, it can be logarithmic in the dimension or in the case of frequency estimation, domain size. In practice, typically just using your system PRG suffices. So say 256, which is very low amount of communication and practical for practical purposes. But maybe what's important that one doesn't always have to use this kind of general compression with general PRG. We show that that for many specific problems, with specific randomizers, one can use simpler unconditional de-randomizers for those which are tailored to that problem that may take potentially even smaller seed and will not require any assumptions, any cryptographic assumptions. So that's the sort of this overview of the result. Let me tell you a bit more about the algorithm, how we achieve it, and then I'll also say a little bit about the analysis. So the algorithm, let me just start with just a couple of definitions. As I mentioned, we'll have a randomizer, which is epsilon differentially private, and we'll fix some input element to that randomizer. For example, it could be just a vector 0 or just the main element 1. We'll fix and refer to that elements by x0. And as I hope you remember that we know that the ratio of densities of output of our randomizer on any input x to its density on this element x0 is at most e to the epsilon. This is the property we'll use in a second, but just a quick reminder of that of the main property of epsilon local differentially private randomizers. So now, having fixed the element x0, will denote the algorithm which samples from the distribution, the same distribution as our randomizer applied to this input x0. X0 will refer to it by R0. And it's just a randomized algorithm which samples from this fixed distribution because we fixed the element. And because it's a randomized algorithm, well, the way we think of a randomized algorithm as basically an algorithm which gets as an input a sequence of bits and outputs, bits, coin flips, and outputs some element in domain Y. So that if it is fed a random and uniform sequence of bits, it will output a random and uniform element in sample from this distribution R of x0. So basically, just as a fixed randomized algorithm, we can think of it as mapping a sequence of random bits to some output. So now we will be interested in using, instead of the true random bits, which the algorithm might require a lot of those, we'll be replacing those with pseudo-random bits. So we'll need the PRG, which is just an algorithm which takes a short seed, which we think of it as having length L, and mapping it to a long sequence of random bits of length T, where T is the same as the input, is the input to our algorithm R0, which creates this reference distribution. So that's the notation that I'll need. So the algorithm, which maybe one should think of it as pseudo-random rejection sampling, is one can think of it as based on an idea which is implicit in the work of Mishra and Sandler from quite a while back. Although rejection sampling for local randomizer has been used in a different way in a few other works. So it works as follows. First of all, maybe you can think of it as consisting as two ideas. The first idea is, instead of directly sampling from the running our randomizer, we'll always will perform rejection sampling. We'll have some reference distribution, which is just the sample randomizer on some fixed input x0, and because this distribution is, we know, to be somewhat close to the desired distribution, which is the distribution on R on input x, we can produce a sample from the desired distribution by doing rejection sampling relative to the reference distribution. So this is just doesn't change anything, but just a different way to sample from the same distribution. But now, having replaced sampling, once we produce samples using this rejection sample, instead of sampling from the original reference distribution, we can replace. So we know that, again, the sample from the original distribution can be produced by feeding a long string of truly random bits. We'll replace those truly random bits with a pseudorandom seed, and then we'll basically we'll be sampling from a pseudorandom version of the reference distribution, and then we'll do a rejection sampling relative to that. So it's very simple. So here is actually the entire pseudocode. We start with this randomizer, and it's kind of parameterized by access to some pseudorandom number generator G and some failure parameter gamma, because rejection sampling has sometimes failure probability. So we'll take this some number of repetitions that we need to try, which is just e to the epsilon times this ln of the of 1 over the failure probability. And we'll repeat the following loop, in which we'll sample a random seed. We'll convert that random seed. You will use that short random seed. We'll feed it to the PRG, get a long sequence of random bits. Then from that long sequence of random bits, we'll create a sample from our reference distribution, R0. Now we'll perform rejection sampling on that sample, which is just we'll flip the coin with this ratio of densities of our reference distribution to the desired distribution R of X. We'll scale by e to the epsilon, and the property of local randomizers that this ratio never exceeds e to the epsilon ensures that this is a valid. This ratio is at most 1, so we can flip a coin with this bias. And now if that coin outputs 1, then we'll break the loop, accept the seed, and output that seed. So that's just standard rejection sampling, but with a PRG. And it's not hard to convince yourself that this should behave as desired, but I'll explain why it actually works. So on some level, computation that it should produce a result which is computationally indistinguishable. This is, again, very easy, relatively easy to see, slightly harder to see that it preserves privacy. So let me mention that there is, so the decoding procedure is very simple in this case. We, on input, which is the seed, we apply the PRG to convert the seed to a long string, and then apply this R0 algorithm to convert it to an output element. So we need to decode the strings, and this is all that needs to be done. And computationally, there is some price that we pay. Basically, we need to run this this reference. We need to sample from this reference distribution e to the epsilon times. So instead of just maybe running the algorithm once, as in the original version, we run it in expectation e to the epsilon times, which, as I'll discuss later, can be somewhat problematic when the dimension is large and the epsilon is relatively large, let's say 8 or 10. So that's the algorithm. Let me briefly describe how we analyze the privacy of this algorithm. And the analysis of the privacy is based on this sort of standard notion in cryptography of fooling. And for this purpose, we first think of tests. And a test is just an algorithm which takes in a random string, takes a string of bits and tries to tell whether that string is truly random or pseudo-random. So it's called a distinguishing test. It just outputs 1, let's say, if the string is truly random, and 0 means that it's not a truly random. And the PRG is said to beta fool a family of tests. if for every distinguishing test, for every attempt to tell whether the string is random, in that family, the probability that the test outputs 1 when fed, the difference between the probability that the test outputs 1 when fed the truly random string, this r from 0 to the t, and probability that it outputs 1 when it's fed a pseudo-random string where we sample random seed uniformly and then run the test on the string generated by the PRG. The difference in those two probabilities is at most beta. Basically, no test can tell with advantage larger than beta that this string is not truly random. So now this is the notion of fooling. Now what we prove that if we're given a PRG G, that beta fools the following family of distinguishers, and this family of distinguishers is just defined in the following way. We define all. We look at algorithms which basically look at certain ratio of densities of our two randomizer to some kind of reference density, compare it with some value, whether this is larger, whether basically it outputs 1 if that value is larger than some parameter theta. So we look at all the tests that can be obtained by taking an input element, some threshold parameter theta. Now, if we if we have a PRG G that can beta fool this family of tests, then the resulting the randomizers that we obtain from our procedure will be epsilon plus 2 e to the epsilon beta local DP. So if basically what this means that if under standard cryptographic assumptions, if our local randomizers, it's sort of density computation can be done efficiently, then the sort of standard PRG, cryptographic PRGs will beta fool them with beta, which is exponentially small, which means that we will effectively get local randomizers, which is with essentially the same privacy parameter. And as I mentioned, for specific randomizers, one can often fool these families of tests unconditionally and with beta equal to 0, not even exponentially small, so without any loss whatsoever. So that's how we prove the privacy. And preservation of utility is actually much simpler in this case. It's just because we are basically just replacing true randomness with pseudo randomness in the process. So we get that the result has to be computationally indistinguishable.
Can I ask a question, Vitaly?
Yes.
So where does gamma come in? This applies no matter what gamma you choose?
Good question. Gamma will appear in this preservation of utility. It will be preservation of utility will also get the statistical distance. So gamma will enter in the in utility. It doesn't affect privacy.
Okay,
but because you may fail, when you fail, you still remain private, but you sample from now we will be sampling from the reference distribution instead of the original one. So you pay, in utility you have to pay.
Somehow, like the privacy guarantee uses both sources of randomness, meaning both the choice of the seed and the Bernoulli coin flip.
Yeah, but you're right. But in this algorithm, basically, when you fail, you're sampling from the reference distribution. So you're basically mixing in the original distribution. So one of the input so even when you fail, you're sampling from.
Oh, I see. Okay, yeah, I guess I hadn't quite parsed that from the pseudocode, but I see. if you get to the end and you haven't accepted, you just output a
basically,
sample.
Effectively, you end up sampling from the reference distribution in this case. Yes.
I see. Okay. And so that, yeah, so that mixture, doesn't affect privacy. It's just a
Right.
message.
Mhm.
I see. All right. But you do need you need the PRG to be good for this particular family in order to get the privacy analysis to go through. And
Yes.
I'm just trying to wrap my head around how this compares to other approaches, which were using the PR. I guess they I'm thinking of some of the approaches where the you've got some sort of public randomness.
Yeah. So it's actually a different approach. Maybe it is worth mentioning that even without any assumptions on PRG, effectively, basically any PRG that you feed will give you 2 epsilon privacy, just without any assumption. So you and I think in those approaches that you're describing, the loss was always at least to 2 epsilon. Of course, you need to preserve utility, which means that you cannot quite use any PRG. But basically, for any PRG, if you only care about, so maybe the comparison is that these analysis that you're talking about with public randomness, they're different in more than one way, but one similarity between them is that if you do not use any PRG properties, you get a similar blow up in the epsilon, which is kind of something that is important to avoid in this, again, for 2 reasons. Because first of all, because we're in this epsilon larger than 1 regime, where doubling the epsilon is bad. And also because we want to be in the end, we want to be optimal up to a constant, including the constant star.
But here the way you've written it on the slide, the beta is big. The privacy cost.
Yes, it's right. The way it's an upper bound. Yes.
I see. Okay. So you're saying, the thing you're saying, which is not written on the slide, is that even if beta is big, the actual expression for the parameter is bounded by 2 epsilon or something.
Right. And that's again, that is actually very simple. Very simple analysis, just because
I believe you.
Just the normalizing factor changes by at most epsilon and the original one.
I see.
So it's anyway. Thanks for keeping whatever I say straight. Okay, so that's all that I had time to say about the analysis. And in the interest of time, let me go to some applications. So first, the frequency estimation. And for this purposes, let me briefly remind you what the Rapport algorithm does. And the algorithm works as follows. It takes as an input some j, which is in the main, which is the number from 1 to k. It first replaces it by the indicator vector, which is just a vector of length k, 1 in position k, and then replaces that 1 in the sequence with a random coin flip with bias 1/2, and it places 0 with again a coin flip, but now with bias 1 over the e to the epsilon plus 1, and all of those are done randomly and independently. And it's very easy to see that this algorithm it's easy to see that it's epsilon differentially private. It's not hard to prove, or at least that it achieves this optimal privacy utility trade-off that I've mentioned. But of course, it has this, the problem is that the number of, if you were to send the output of this algorithm, its length is k, although of course maybe you can compress it somewhat, but still it's very long. But what is relatively easy to observe, and what we use to define this new algorithm, we call it pairwise independent rapport, is that in order to preserve the privacy guarantees, so basically when we can think of this output domain as being all strings, all 0-1 strings. But in order to preserve these privacy and utility guarantees, it's sufficient to make sure that that we have a family of strings of this, which is pairwise independent and has the right biases. So any family which has the same biases as the rapport and has zeros and each pair of bits is in that string is pairwise independent, will preserve both the privacy and utility. In fact, for utility, you need the pairwise independence, and for privacy, you only need the biases are correct. And now we can use completely standard constructions from sort of the area of using random number generator to create such bit strings with short description. Specifically, one can use subspaces of a vector space over a finite field. And again, this is completely standard and gives a construction which communicates only order epsilon plus log k bits, achieves this same optimal privacy utility trade-off, and has a kind of roughly the same runtime as the original rapport, although it can be a little bit better if k is smaller than n, then it can be improved to runtime can be improved to n plus k squared instead of n k over e to the epsilon. So that's sort of an immediate application. Its kind of only downside is somewhat poor server runtime, which is worse than some of the algorithms that have been known. So this is why myself, Hui, Jelani, and Kunal have looked at ways to improve it. And we improved it using a so-called projective geometry response. And I won't have time to go into the detail, but basically we'll look in so-called projective space of the, again, a finite vector space over finite field, this f q to the t, with q chosen and q and the dimension chosen to be sufficiently large. And this projective space is basically, one way to think about it is the set of all equivalence classes among these vectors over finite field, where equivalent two vectors are considered equivalent if one can be obtained from the other multiplying by a scalar. One can also just associate each equivalence class with an element which has always has one in the first coordinate. It's not particularly important. What's important is that if one looks at these t-dimensional projective subspaces, they form a pairwise independent subset system again, and using now by appropriately choosing the field size and the dimension, plus we also introduce a server-side decoding algorithm, which does it sort of faster than the naive way, using some relatively simple tricks from dynamic programming. We get an algorithm that still communicates, has the same communication as already as pi rapports. A short communication achieves this optimal privacy utility trade-off, and now has server runtime, which is n plus k times e to the epsilon log k. So it avoids this kind of n either k squared or n k terms. And it's not just in theory, we do actually implement it. And here are some of the results for this projective geometry response. So first of all, for maybe some example setting, not particularly hard, it achieves a huge speed up over by Rapport of over 50 times. It's still somewhat slower than the fastest algorithm, although not hugely, but this randomized HR. And let me show you the actual results. So this is just a graph which takes some specific distribution and measures the square error for in reconstructing that distribution, and we do it as a function of epsilon. And here, the bottom two light blue and dark blue lines, I guess are identical, because one of them is the truly optimal algorithm, which is subset selection, and our algorithm. And there, as I mentioned, they both achieve the optimal trade-off, so the curve is the same. And the other lines, the green and the red, are the previous algorithms, both based on this Hadamard response, and they can be for many settings of parameters almost a factor of 2 larger in terms of the error. And the fastest among those is about 5 times faster than our algorithm, but at the expense of the worse error. Yes.
So again, this PGR, the idea is that you're taking a specific pairwise independence family and then running it through the previous. Did I understand correctly? Like you're running your transformation applied to Rapport using this particular generator?
There is one way to think about it through, I mean, you don't have to basically, one way to think about it is that it creates a family of binary strings. We don't actually, I don't know, I guess maybe one can view it equivalently as still de-randomizing the construction. We don't. There are some. We actually do it slightly. No, we actually do it slightly differently. For example, you can optimize. We don't need to perform rejection sampling in this case. We know.
Right. That was actually kind of where I was going. Like, because with things like Rapport and DJW, you can do this thing where you just like pick the public app, pick an output, and then like flip it with some probability that's either like. Right. So that's like I guess also you can think of that as like some better version of the Mishra-Sandler transformation. Is that what you guys are doing here?
I think it's probably, the answer is probably true. There is a version of our algorithm which does maybe what you're referring is that there's a version of algorithm which really in which almost all the communication is public, can be sent as a public string. Only basically one field element is sent as a private. That's yeah, but the sort of, we don't really need it, because even even if you send all field elements, maybe the trick is that you can generate them fast. You don't need to do a rejection sample. It's just because, you will basically picking some of them fully randomly and one just to satisfy the equation, which I believe what you mean.
I think that's slightly different from what I have in mind, but maybe ultimately equivalent. I'm not sure. The thing I had, like one way to think about the Mishra-Sandler transformation, or a variation on it, is you pick one seed, and now either
I see.
And then you send an additional bit, which is,
I understand.
So you send the seed to the server,
right?
And you send one extra bit that tells the server whether or not they should use the output of the generator as is, or flip it. Like
we have a version. That's not what we don't really need that trick for this version of the algorithm, but we actually know that what you're explaining is possible, where you pick fully randomly all but one element, and then one element is chosen just basically it's like flipping, but it's not flipping It's just as it's a random choice of an element from a field of size Q. Anyway, in the interest of time, I do want to try to say a little bit.
Yeah,
about,
okay, we can talk about it later. Yeah, it's fine.
A bit about the mean estimation. So problem and how we apply these ideas to this problem. So first of all, as I mentioned, the optimal, empirically, the optimal algorithm is so-called a priv unit, private unit vector by Balming and others. And this algorithm is parameterized by 3 parameters. And so again, the goal is to privatize a unit vector. It has 3 parameters: the radius, some parameter gamma, and probability p. And it samples, it outputs a random uniform vector in some spherical cap or its complement. And the spherical cap is the spherical cap of a sphere with a radius r. That is where the cap is in the direction of the input vector. And there is a cap, there is a parameter gamma, it defines the offset of the cap. And the probability p defines the probability that you sample either from cap or its complement. So there are 3 parameters, but actually 2 of them are tied because we want to make sure that this entire process is epsilon differentially private. And we also want to ensure that this randomizer is unbiased, meaning that the expectation of the output vector is the input vector. So, and Balming et al. Gave some way to choose the parameters, which ensures, for which they prove that the algorithm is asymptotically optimal. What we have showed with Hilal Esti and Kunal Tovar is that there is a choice of parameter for which this algorithm is truly optimal. And optimal here in the sense that we show that it's optimal as it gives the lowest variance among all unbiased randomizers. We also show that if you want any non-interactive protocol, which is unbiased, it will also, like the protocol based on this algorithm will have the lowest error. So basically, we now know what the optimal algorithm is. So we can basically directly apply our general compression technique. Unfortunately, we are not aware of a sufficiently simple PRG with good parameters that would allow us to get either unconditional or at least not use something simpler. So we do it. We sort of after we can compress it and we get the following results empirically. So here we're comparing the original priv unit algorithm in black line. The green line is our optimized. We just pick the parameters optimally, and we compare it with the 2 sort of previous algorithm. The blue line is the low communication algorithm, which were based on Gaussian representation, and also we compare it with this Ducci et al. Algorithm, which is only optimal for epsilon smaller than 1, and you can see that it does become significantly worse for larger epsilon. And to clarify, this is the graph is the mean squared error as a function of epsilon on the, and maybe I should also mention that it's on a logarithmic scale. So the difference may not look very large, but they are actually like at least a factor of 2 improvements over the best previous algorithm. So that's the improved algorithm. As I mentioned, we can compress it using our technique. The communication is low. The only sort of problem with this approach to compression is it turns out that the rejection sampling itself becomes a bit of a bottleneck when epsilon is relatively large. The client needs to run.
Sorry,
yes.
Can I interrupt to go back to the plot for a second? So, sorry, what's the difference between the bottom 2 curves? What is
okay. Yeah, so as I mentioned, this Balming et al. Gave us priv unit and gave a specific way to pick parameters for that algorithm.
Oh, I see. So like gamma is like the important one, right?
Yeah, gamma and p both, or at least if you pick one, the other will be all fixed. So yeah, so we just show that how we just optimize. We show that if you optimize, you can squeeze out like another
factor of quite a bit. Right. Okay.
It was already the best. It was already best, but we slightly improved.
Understood. Yeah, thanks.
So as I said, we get the algorithm. The only issue with it is that it has this runtime, which the client needs to run the sampler e to the epsilon times, which is for very high dimension is somewhat problematic and raises the natural question of, can you do it faster than e to the epsilon? We did not come up with a faster algorithm, but we found a simple way to trade off between sort of the accuracy and the running time. And the simple way is just repeating the algorithm multiple times. Basically, for some fixed number of repetitions L, we replace the randomizer with budget epsilon with executing the same randomizer L times with the budget, each using a budget of epsilon divided by L, and then averaging the outputs. And this L should be thought of as something small, like 2 or 3 or 4. The goal of using this splitting is, once you split epsilon budget into, say, 3 times, the e to the epsilon factor that one needs to pay in the execution here becomes much smaller. So it becomes computationally much cheaper by using just 2 or 3 repetitions. This does have some kind of cost in terms of accuracy, but at least we know that asymptotically this doesn't make anything worse. It increases the communication a little bit by this factor L, but which is technically usually not a problem. But it preserves asymptotic optimality, but the constant becomes worse. So there's a natural question of how much worse would the constant become. We map it here for the number of, we pick epsilon equal to 8 and look at how does this sort of repeated version behave relative to, say, the best previous fast algorithm, which is SQAQR. And we see that whatever, up to 5 repetitions, our algorithm still performs better. And typically 2 or 3 repetitions would suffice to make it computationally efficient. So that's just a simple way to solve some of the computational issues with the problem, although at the expense of worse constant. So that's all that I wanted to say. Let me go into conclusions. So maybe the basic message is that local differential privacy kind of implies existence of low communication protocols with essentially the same guarantees. Something that I think is an important property that we should be using. Implies that that whatever guarantees we're interested in, at least information theoretically, they can be reconciled with low communication. I mentioned 2 applications: the one for getting algorithms with optimal accuracy for frequency and mean estimation. I did not mention the Gaussian version of PrevUnit. It's very similar. Instead of sampling from the spherical caps, we'll just look at the caps on a Gaussian distribution. It's not the same as adding Gaussian noise, but it's in some ways easier to analyze. In terms of, there are still many remaining good questions. So as I mentioned, we kind of, in a way, we solve the information theoretic part of the question, but turning into efficient algorithm is still an interesting and non-trivial task. We've sort of made progress for this problem for frequency estimation, although even there, maybe even further improvements might be possible. But things are worse for mean estimation, and ideally one would have an algorithm which is computationally efficient, have optimal accuracy, have low communication, being polynomial in epsilon and logarithmic in D, and also have low client running time of just OD without the e to the epsilon overhead. The server time also ideally should be kind of scale reasonable, better than say D times n. That's all that I have to say. Thank you very much for your questions. And if you have any more, please let me know.
have a couple of questions, but I want to let other people. I've already asked a bunch of questions. Okay, just briefly, so for frequency estimation, there's Vitaly, there's also a question of like efficiency in K. Right, so
efficiency
like
of what?
Everything,
Of
but
course,
no,
sure.
server side. So like in your case, the client complexity scales with like log K, right?
Mm-hmm.
But the server still has to like expand out this whole K-bit vector and process that for each client.
Not quite. That's exactly what we were trying to do with this projective geometry response, where you would basically be storing the original compressed representation, and then you basically need to add up those n numbers stored in this compressed representation, and it's not and it's possible to do this in faster than sort of in a naive way expansion. And maybe the best example is these kind of Hadamard based algorithms, where we know that you can do something like DFT or FFT to add up numbers the sort of to add vectors in basically you would be collecting the vectors separately and then multiplying them by the matrix that
like we know of other solutions, other approaches to this frequency estimation problem that can sometimes get complexity that is like even at the server end only log K or polylog K.
Oh, I see. Well, I see. Okay, good.
When
point.
K, like in the setting where K is very big,
I see
like
what you mean.
trying to identify new words or new, your URLs that are being queried or something like that.
Right. You're right. So you're talking about some like actually going back to this heavy hitters type problems where you
more the heavy hitters type setting.
Yes, you're right. In most problems, K would be too large or at least many problems, K would be too large for anything. In this case, you would be using some kind of whatever, one of your heavy hitters algorithms or other people's. But basically most of those algorithms as a kind of a primitive building block, you would be using a frequency estimator over some kind of hashed thing. So you can pretty much plug these kind of this sort of So you can think of it as a basic building block for all these algorithms is a frequency estimator where the domain is not too large. But and in fact, some of these algorithms are described in such a way as a reduction between a sort of a frequency estimator
I may have even written some of I get that.
I know.
Wait, can I ask my question?
Sorry.
So the question is that, like, if you do that, then in a lot of those transformations, you're giving up some additional small loss, like an additional log K factor or something like that. For at least the way I have them in my head, maybe one doesn't have to. I guess my question is that, like, once you're after optimality of constants, then it suggests that there's like a question. There's like, can you get this logarithmic runtime at the server on the server end, and still get like this sort of strong sense of optimality that you're aiming for?
I think that then for these problems, I believe there are algorithms which don't lose logarithmic factors. That show that you need to pay these logarithmic factors. Of course, in this setting, it is no longer known what the optimal constant. Although, asymptotically, I think we do know that some of these, how to achieve the asymptotically optimal error. And I believe it does have this log k factor in this case.
It does, but I don't know if
and I'm saying like
people-
it's upper and lower bound,
Constants.
both need, but the constants is the setting.
That's correct. Right, but it's not clear to me that the constants are tight. on
Right.
Any of those. Right. So I guess that's, like, can you get away with, can you get like can one analyze and get to the same sort of strong sense of optimality of like exact constants that you have?
Yeah, it's a excellent question. Whether it's sort of a optimal algorithm for this huge domain. That is. I like the question. I don't know the answer.
Okay, right, great, thanks.
Any other questions? So let's thank Vitaly one more time.
Thank you.
Thank you, Vitaly, and hopefully, we'll have you again sometime, maybe even in person. But
I was also hoping, but somehow things are a little more complicated. But I was initially hoping to actually get myself to Boston, but hopefully there'll be other opportunities, and hope many of you will visit.
All right.
Thank
Thanks.
you.
Let's thank Vitaly again, and we'll see. I think the next talk is May 23rd. Is that right? With Frauke Kreuter will be speaking, and that's in 2 weeks. Yeah, that's right. 2 weeks from now. All right. See you guys then. Bye.
Bye-bye.